Here we go. So we're talking about inverses, inverse functions. So the first thing I want to get across to you is that this is the symbol for an inverse. And this is f, and this is the inverse of f. Okay? And what they're showing here is that the domain, which is what you input, and the range flip-flop. Look at this range becomes the domain, and the domain becomes the range. And that means that in an inverse, the x becomes the y, and the y becomes the x. So if I gave you y equals negative 2x, could you graph that? Everybody graph that quick. I always want to be able to show you the equation and the graph of the equation to kind of make sure you get what we're talking about in a visual way. Okay, so here's negative 2x. Negative x would have been this. That would have been a negative 1 slope. Okay, but here's negative 2x. Goes a little steeper. All right. Now, do you know the line y equals x? Everybody graph that in green. We'll make it a dotted line. The line y equals x. Now this is going to be hard for some of you. But you'd have to do a reflection across that line. All right, so this part, let's say that we put in negative 2. If I put in negative 2 in the function, I get negative 2 times negative 2 is y equals positive 4. So this spot right here must be negative 2 comma positive 4. Now, if the x and the y really switch around, then the x becomes the y and the y becomes the x. So the new point that would be across this thing, straight across it, going straight across here, would be at, well, if it's just x and y switched, it's just x and y switched, 4 comma negative 2. Does that make sense to you? This is y became the x, and the x became the y. All right, let's pick another spot. Would you agree that the point 1 comma negative 2 would be on here? 1 comma negative 2 would be on here. Then what other point would be on the inverse? Flip them around. Negative 2 comma 1. Negative 2 comma 1 would be on here. The black one and the red one are a reflection over the green line. That is inverses in a picture. It's a reflection across the line. So if I tell you I've got a function and it's got a point 2 comma 8 on it, you can be assured that if on the inverse there will be the point what? 8 comma 2. You just have to flip them around. Okay, so I better make this point look like it's in the right spot. 2 comma 8. I put it in a weird spot. Over 2, up 8. There'd be 2 comma 8. It would have the point 8 comma 2 on it, which is over 3, 4, 5, 6, 7, 8. Comma up 2. I'm going to put a dot with maybe a different color. That's the inverse of 2, 8 is 8, 2. X's and Y's switch around. That's all there is to it. If I make this line, this dotted line here, it'll be a reflection straight across that line. Now, if it's not exactly straight across, it's because I didn't make this on graph paper, and so it isn't lining up perfect. But all right. Next thing, if I give you an equation, y equals 3x plus 7, and I want its inverse, then Here's the process. You switch x and y, and I go x equals 3y plus 7, and it's not quite that easy, but it's pretty close. You just got to solve it for y now. Because you can't really compare a y equals and an x equals equation. So now you just solve this thing. So you switch x and y and you solve it. That's it. Minus 7, everybody do that. You got x minus 7 equals 3y. I'm almost solved. Let's solve it. Divide by 3. I like to divide it by 3 in all the parts. And now I really like to have the y on the left. So I'm just going to say y equals over here instead of over here. Okay? So there's the inverse. This one and this one are inverses of each other. Where this one multiplied by 3, this one divides by 3. But the thing that might mess with your head is that where this one adds 7, this one doesn't just subtract 7. This one subtracts 7/3. But if we had done it this way, if we had gone just divide by 3 under the whole thing, I think you get that we could have done it that way, then it looks more like what you'd expect. Add 7 becomes minus 7, and times 3 becomes divide 3. Inverses. So imagine it's the test, and I say, here is a function. Would you agree that that passes a vertical line test since it's a function? Okay. Then would you please sketch it for me? And then when you're ready, when you've got this copied, try to reflect it across that line of y equals x and see what its inverse would look like. Now, if it was a test, I'd encourage you to pick a few points on here. Like, I know 0, 0 is on there, but that doesn't really help because if you switch 0, 0 around, it's still 0, 0. But I would actually make up some points, and I go, well, that, to me, that looks like, I don't know, 2, 4 right there. You know why that's helpful? Because then you can go and graph 4, 2. You know what I mean? If I say that looks like 2, 4, then that looks maybe more like 4, 4 would have been right there. So, because it's on that line y equals x, right? 4, 4 would be right on the line. Now, flipping it around, though, it's there. Well, I guess it's helpful to know that there is a point on the inverse that's right there. So some of you are going to be like, well, yeah, naturally, Mr. Server, that's easy. And other people are going to be like, I can't do that. My wife is one of those. She was a valedictorian of her high school class. She is very bright. But she hates this kind of, like doing things in 3D or doing things and having to visualize what's going to happen when I flip this across this line. She just hates that kind of stuff. So some people are naturally good at it, and some people aren't. Okay. What's that green thing? It's the inverse of the blue thing. I don't even know what the blue function was. We don't have to know. We can just go, any point that was on the blue one, there must be a comparable point across here. Like here, let me show you. Right through there. Instead of 2, 4, that must be 4, 2. All right. And on one of our tests, didn't we ask you to find the range and the domain of a graph like this? Yes, we did. That blue one, focus on the blue one right now. If this is 1, -3 down here, then would you please tell me the domain and the range of the blue one? Domain, range. Range is low to high. Would you please compare the domain and the range with the kid sitting next to you? I'm going to pause for a second. Thank you. It should be -1, -3 down there. My bad. Sorry. That's -1, -3. That makes a lot more sense in the picture. So, yeah, you're going to have to change. Well, I can tell you right now, you aren't going to change your range because I changed an x. So since I just changed an x number, that should change your domain. I understand. Hope you like the place. All right, so domain should have been from -1, and I apologize for missing that negative. -1 to 4. And I do see solid dots, so I should probably put brackets on it, because there weren't empty dots, they were solid dots. And then the range, the lowest it went was -3. Really easy to get those confused. You got to talk yourself through it. Like, is it the x or the y? The range is about the y's. -3 to 4. Okay, cool. So that's the domain and range of the blue one. Without having to even think about it, you should be able to tell me the domain and range of the green one. I mean, you have to think, but you don't have to like, well, we can't see the points on the green one. You don't need the points on the green one. The domain and range of the green one, since they're inverses. All right, give it your best shot. What are the domain and range of the green ones for the green one, which is an inverse of the blue one? All right, did you figure out that the domain becomes the range? And therefore this is -1, 4. And that the range becomes the domain, which is -3, 4. Oh, bracket. There. Make sense? Domain and range switch around. X and Y switch around. A lot of switching around going on here. This is a flip across that red dotted line. That's about everything you need to know about inverses. Now we'll just kind of go through the slides, and I hope that you'll understand it and it won't be. All right. They're saying the domain of a function, of the f function, would be the range of the inverse of that function. Remember me telling you the little -1? If this is f of x, then f -1 of x means its inverse. If you switch x and y and you solve for y, you are finding the inverse. Showed you one of those. Inverse functions can be drawn by reflecting that about or across the line y equals x. So let's do it. Let's say you had this one. Y equals x squared. Notice how I said y? Do you get if you can't switch x and y unless you have a y in the equation? So I'm making it a y. Okay, then we're going to switch them. X equals y squared. Do you remember me telling you that that was a sideways parabola? So this freaks people out a little bit. How do you flip that across this line? By doing that. The black one and the green one. I know I didn't do it perfect. Those are inverses of each other. If I had to prove it on just one point, I'd say, well, 2, 4 would be on this graph. And look, 4, 2 is on that graph. And again, I'm not graphing it perfectly. These are just sketches. But the green one is this here. This guy right here I did in green. And this guy right here I did in black. Don't have a purple pen anyways. Okay. And all you have to do is switch x and y. Now, you are supposed to solve for y. So I'm not quite done with this yet. On the test, I'd have to solve that for y. So when I go square root, I get absolute value of y. Remember me saying that was going to come up? Yep, I did. And I just now have to split it into two things. Y is equal to the square root of x, and y is equal to the opposite of the square root of x. And that's why the green thing is not a function. Do you get how the green thing would not pass a vertical line test? Do you get it also has two equations for it? The top part and the bottom part are separate. Yes?
So do we have to write the absolute value sign?
Absolutely.
Or can we write
No,
plus or minus?
you need to write the absolute value sign. Otherwise, you don't really understand it. I'm trying to make this a point because so many kids go, well, I was taught this. And the square root of 9 is plus and minus 3. But it's not. You're lying to yourself. And then you're skipping a whole step and just saying that the square root of x squared is x, and it's not. The square root of x squared, if you graph it, it's a v shape. It's the absolute value. That's why you have to show the absolute value in there. And the square root of 9 is just one thing. It's already happened to kids on the tests where they were evaluating a function and the function had a square root, and like there's a square root of, 2x minus 3, and they end up coming up with like, they stick in a number and they get the square root of 16, and then they go, oh, so the answer is plus and minus 4. Oh, it's not. It's just 4. You can't put a negative answer for that. So that's why I react strongly when somebody just says, can I just say plus and minus? No, you can't. There is only one square root of 16. Now, when you get into super high level math, then you can start playing around with, whether there's a negative square root of it. But for one thing, this symbol is called the principal square root. And if you look up what that means the positive forces it to be positive square root of 9. Okay, so back to inverses. Let's go to the next page. Get to this yellow-ish or whatever color that is. Orangey, yellow, tan? Ugh, I don't even know. Here's our parabola. Here's our sideways parabola. One of them's y equals x squared. And the other one is, to switch it around, x equals y squared. Here's the example I started with a line, flipping a line across this line y equals x. Those can be hard to think through. But this one, the blue one, and the green one, those are inverses of each other. I can tell just by looking at it. If I wanted to get some points, whatever that point would be the exact reverse of this point. Like 2 comma 6 turns into 6 comma 2. Just switch the x and the y. All right. So, I'd like you to zoom in on this one. And I'd like you to draw me an inverse of that red function right there. Hint, put in the line y equals x as a dotted line. It'll help. And then draw me the inverse. The fact that they gave you 3 points really helps. And if they hadn't given you 3 points, I would have made up 3 points. And in an area where there isn't a point, I would make up one. Like, that to me looks like, well, if this is -8, then it's a little further, so it must be like -9. So that point right there, I could just make one up and say, I think that's -9, comma, down, I don't know, how far is 4 in their mind? They say this is 4. Well, and that's down even further than that, so maybe this is -9, -6. There, I just made up a point that you could use when you're making your inverse. This inverses thing is such a big deal that when I had to pass a test on calculus, this was one of the questions that they gave me. They had like a million choices they could give me. This is to get my national board certification. And they asked me something about inverses. So I had to answer this. Ironically, I teach it, and I had to answer a kind of complicated question about inverses. So this is an important topic. Okay, Haven, can you tell me what if there's a 4 comma 9 on this one, what does that tell you? There's a 9 comma 4 on the other one. And if you look, you should make it be like, oh, look, it's straight across that line. Again, I'm not perfect. You aren't either, but that's good enough. And if there's a 0 comma 4, Mr. Globe, E, then what is there on the other one? 4 comma 0. It's like there. And what does it do between here and there? Well, if you really, really want, you could pick a point that's in between them and say, I'm going to make up what that is. I'm going to say that's over 2 because it's, halfway to the 4. And then it's up, it looks like maybe 6. Then 6 comma 2 would be on this one. Now, how about this negative 8, 0? Well, then there's a 0, negative 8. So then down here, there-ish, looking straight across the line there, right? And then this curvy thing is bothering me, so I'm going to make up a point in here. I'm going to say that that's negative 4, comma, it looks about the same height actually. Negative 4, comma 4. Really helps. Now I can just go 4, comma negative 4. There-ish. Oh, so it goes like that. Is it perfect? No. Would I have given myself credit on the test? Yup. And notice, to really try to make sure I did this a decent job of this, I made this point and I made this point up. They don't have to be perfect, but at least that'll get you a lot closer than just freehanding it. All right, let's move on to the next slide. So, this is kind of a combo of the last 2 days and today. This function, make g of f of x. Everybody do that, please. Figure out the answer to that. Then I just taught you how to find inverses by switching x and y around. So remember, it has to be solved for y and make me the inverse of g. And then last but not least, find f of the inverse of g of 5. Don't try to start with the end. You can't. You got to find the inverse of g before you can possibly do part C. So you have to do B before C. I recommend you do A, and then you do B, and then you do C. I'll pause for a minute. You can try those. Okay. G function, which was x plus 3, eats the f function. There's the f function. It eats that. So 7 minus 2x. And if you simplify that down, you get negative 2x plus 10. Did I have that right? Negative 2x plus 10? Is that what you guys had? Okay, good. Then the inverse of the g, here's the g function in the first place. Y equals x plus 3. Notice me using y instead of g of x. And then I flip-flop them. X equals y plus 3. And can I just leave it that way? No, you have to solve for y. So then it's y equals x minus 3. And if you just think about it, x plus 3, x minus 3, it makes sense. They are inverses of each other. Okay. All right, next is this one. Well, now that I know what inverse of g is, that's this, then I'm supposed to stick a 5 in there. Well, it's not too hard. So I'm going to stick a 5 right there. 5 minus 3 is 2. So I got 2. That's 2. Then it's just f of 2. And f of 2, I go back to the f function is there. And it's 7 minus 2x, and the x is 2. So this is a 2. 7 minus 4 is 3. Raise your hand if you had a 3. Okay, good. There, you've learned inverses. Yay. Is there more? Well, there is, but most of what I've taught you is just going to get more complicated with more complicated algebra. Okay? So let's say it's this, and I got to find the inverse of that. Ew. Well, first, they want me to write it like this. They want me to basically write it in, as a vertex form. Very good. All right. So, can anybody remember, oh boy, it's been a while, how to change this kind of a thing into that? Y equals x squared minus 6x plus 13. They want it to be something like this. Y equals like x minus 4 squared. That's, I'm not saying that's the right answer. Plus 9. You probably haven't done this since like one of your hardest ever algebra tests. It was called completing the square. Can anybody remember how to do it? Ooh, a bunch of hands go up. All right, Anjali.
So first you divide the negative 6 by 2.
Okay, for those of you that are like just watching, please get ready to write. So we're going to do x, and I'm going to go x squared minus, and you just said you wanted to divide this by 2, so you're starting off right. You take half of that, which makes half of negative 6 is negative 3, and then what do you do?
Then you find what negative 3 is squared.
Okay, so half of that and squared. If you just say it as one word, it's going to be dumb, but you're going to use it multiple times this year. Half and squared. So if I take negative 6 and do half and squared, what is half of negative 6?
9.
Negative 3. And then squared? 9. It's 9. So 9 is the magic number. Everybody write negative 6x plus 9. But wait, Mr. Server, you just changed a 13 into a 9. Can you do that? No. So here's how you can make that right. I just added 9 here because this part right here now will factor. And if you can factor it, you should. So why did I pick 9? Because it would work really nice. But that means I have to also subtract 9 to even it out. You're used to adding 9 on both sides. Would you agree if I add 9 on the one side, I got to add 9 to the other side? But do you get if I add 9 over here, it's just like subtracting 9 over there? See the plus 9 and the minus 9? Won't they cancel each other out? Yes, they will. And then the 13 is still there at the end. Okay, so we basically just took that original equation, here, here, and here, and it's still here. It's there, and it's there, and we just had to put this plus 9 and the minus 9 into it. That's called complete the square. And I know that's really intense, but that's going to help us on a future day that I kind of reminded you how that worked here. And I'll show you why we did it. Because look, x minus 3 squared, because that's what this factors to, is x minus 3 and x minus 3. If you're not good at factoring, you got to get good at factoring. That's why you need that top 20 to be awesome for everybody. If I was going to make a top 20 part 2, this would be on it. Okay, so anyway, I've had kids tell me before that this problem, complete the square, was the secret for them on the PSAT. They realized, oh my gosh, I can complete the square, and they ended up figuring it out, and they got it, and they made it by 1 point, and they know that they got national merit because of remembering this skill. I know that's a lot, but all right. So I know some of you are just like, I don't even get this skill yet. It's okay, you'll get it eventually. What do negative 9 and 13 make? Plus 4. So there. Why is this any better than it was in the first place? Because it's in vertex form, which means the vertex of the parabola is 3 comma negative 4. So much algebra, remember, in this class.
3, 4.
You're right. I don't switch both of them. Sorry, 3 comma 4. So that's vertex form of the parabola because it's got the vertex built into it. Why did I not trust this one? Because it was on the inside. And I should have trusted this one, and I was thinking I was going to switch both of them, but no. I trust the one on the outside, so that 4 stays there. So it's 3 comma 4 was the vertex of the parabola. Oh my gosh, all of that just in the middle of a regular pre-calc question? Yup. Now, I don't even want to continue this question. I wanted to stop and make sure that you really got complete the square. Y equals x squared plus 10x, and I'm just going to keep it simple, say plus 1, because now you're going to go, there's no way to factor that, is there? No, there isn't. There's no way to factor that. So, what you do is you go x squared plus 10x, and then you use that half and squared thing, and I'm going to put the plus 1 at the end. The half and then squared will tell you what magic number you want here, so it will factor. Take half of the 10, square it, that's the magic number you wanted, and then you have to subtract it again. If you add it, then you immediately have to subtract it. Those have to be opposites of each other on those two red lines. Did you figure out I was talking about plus 25? And then therefore minus 25? And this part factors? And if you can factor it, you should. So many sayings, Mr. Server. Yes, because they help. Okay. What did we just do? We changed it from being a quadratic that was written in standard form to a quadratic in vertex form. And then the vertex is there and there. You just got to be a little careful. It's not 5 comma negative 24. It is negative 5 comma negative 24. That's the vertex of that parabola. When would you ever care about the vertex? Well, it's the one spot on the whole parabola that's special. Think about it. I mean, everybody's special in their own special way, but there's only one vertex. All the other ones are a part of the curve. Okay, that's the one spot where it changes direction. It's the low spot. It's also called the minimum. It's also called the absolute minimum. If I flip the parabola over, it would be the maximum or the absolute maximum. So there's a lot of reasons that the vertex is important. Okay. That is the same as this. If I graph them, they give me the same parabola. Because I didn't break any rules on math, I just rearranged it a little bit. But that's the same as this. It's just this is written in a way that tells me the vertex, and this is not written in a way that tells me the vertex. This way just tells me the y-intercept. This one doesn't tell me the y-intercept. So, you know, there was one good thing about this standard form. It also tells me A, B, and C. So if I was going to use the quadratic formula, A is 1, B is 10, C is 1. There's a little review of algebra from higher algebra that you learned last year and completely forgot until now. Okay. So if I give you 1 without any help, can you please do complete the square? Because that wouldn't factor. But you can add something and then subtract something to make it factor. And then you can write it in vertex form with complete the square. Pausing. Half and squared. Half and square. Half and 2 and then squared is 4. Okay, so y equals x squared plus 4x, and then I'm changing colors just because it's a momentous occasion, plus 4, and then I'm going to use minus 4 in blue, and then this plus 1 is still in red because it was in the original problem. And that black and the blue were both brought in because that would factor perfectly, and this cancels that, so yay, if you factored it right, x plus 2 quantity squared, and those two together make minus 3. Raise your hand if you had that one right. Cool. That's called complete the square. All right, that is as much as I needed to teach you for today. Congratulations. We have reached the end. So now I'm going to get to the end and show you some homework problems. Here's some homework problems. Now, I'm going to narrow it down, of course. All right, there's one more concept I see, and this is one of the reasons I start the homework with you, is it reminds me of something I didn't talk about, and that is called a one-to-one function. All right, so here's what that means. If I've got a function, y equals 2x plus 6, would you agree that is a function? Because you can tell because it's got only one y. Y equals this. Done. I could also graph it and see that it passes a vertical line test, but I don't have to. It just has one y. And if I get its inverse, let's do its inverse real quick. X equals 2y plus 6, and then solve. X minus 6 equals 2y, divide by 2, divide by 2. There it is. Did it solve for y, and is there only one y? So this is a function also. You might think it would always be a function, but it's not. So this one was a function, and its inverse was a function. That's called a one-to-one function. If it's a function, and it has a inverse that's also a function, then it's a one-to-one function. Now, I'll give you one that is not one-to-one. Y equals x squared, and x equals y squared. You know why? Because that won't be a function, because when you solve it, you'll have two things, right? So this is a function, but its inverse is not a function. So that is not a one-to-one function. That is just a normal function. It's not a special one called a one-to-one. Yes?
Are all linear functions one-to-one?
I think I'm going to let... I hate to say alls and nevers, but I get what you're driving at is probably true, but I'm not going to verify it. You have to decide for yourself. And I can tell you this, that just because something is a straight line doesn't mean it's even a function. Think about a vertical line. So the alwayses and nevers are never good for the teacher to say. Okay? So a vertical line is a straight line, but it also isn't even a function itself. So if it's not a function itself, it's definitely not a one-to-one function. All right, so what's a one-to-one function? It has an inverse that's also a function. And you know how you can tell from a picture? Would you agree that that passes the vertical line test? If I made a horizontal line, it would not pass the horizontal line test. What? I never heard of the horizontal line test. You're right. There wasn't one before, but now there is. Because if this thing is going to be a one-to-one function, it'll have to be a function in the first place, which is the vertical line test. And it also has to be one that would pass the horizontal line test. So this red function, it's a function, but it's not a one-to-one function. To be one-to-one, you have to pass both the vertical and the horizontal line tests. So you tell me, here's a function. Well, that's not even a function in the first place, so it's certainly not a one-to-one function, right? Because it doesn't pass a vertical line test. All right, here's a function. Would that pass the vertical and the horizontal line tests? Then it's a one-to-one function. But see, when you look at the equations, it's harder. Is that a function? Yeah, I know that for sure. Is its inverse going to be a function? Nope. Because right away you can see a y in here and an x there, and you can go, oh, nope, that's not going to be a function. But sometimes they're harder to tell than that. And my best advice is see if its inverse is a function. And once you know for sure if its inverse is a function, then it's a one-to-one function. Okay, so back to this. I think you should cross this one off. It's unnecessarily tricky. I don't think we need this one or this one. So that just leaves 2 and 4 on that page. So how am I supposed to switch this and find its inverse? This is a y, right? Then switch x and y around. That's going to be the x, that's going to be the y, and you solve for y. It's just going to be a little complicated sometimes. And you know you'll get stuck at some point. I guarantee you, if you actually do your homework, you're going to get stuck at some point. And then think about my favorite saying, because that's what will save the day. On the complicated ones, it'll become a factoring problem, and a lot of people won't notice. All right. This one, I think you should do, they're still asking for the same thing, right? I'll even tell you, it's number 15. You'll be in the middle of problem 15, and you'll be like, how the heck am I supposed to solve for y? It'll be about factoring. Same with 17. All right, let's even do one together. Before we wrap it up, let's do one together. This one right here. Let's do number 15. It's part of your homework. It counts. You can grade it, but I'm just going to help. So if this is really y, then I'm going to flip-flop. I'm going to say x equals 3 over 4 minus y. Now, first rule is if you can factor it, you should. Can you factor it at this moment? No. Second rule is, can you clear fractions out? Is there a fraction? Yeah, can I clear it? Yeah, I can multiply by what? 4 minus y on both sides. Okay. That cancels that. That got messy, but I'm going to write it out. 4x minus yx is equal to 3. Now, oh wait, it's actually number 17. But I know it's going to be important for your future. So this one you won't have to factor it because there's only one y. Imagine a world in which there was a y here and then there was a y here, except it would be like 3y or something like that. You'll have that in this problem and this problem. So actually I'm going to do it that way. Okay, so wait a minute. I'm going to finish this problem right because we got to finish this problem. So then I'm going to subtract 4x from both sides. Negative yx is equal to 3 minus 4x. And then I'm going to divide both sides, trying to solve for y here, by negative x. Divide it by negative x. And the negative cancels and the x cancels, and it's solved for y. That one wasn't even that weird. That was number 15. I'm glad I actually talked to you about it, though, because in number 17, that's the one where when you're in the middle of solving that, you will end up with 2 y's, and you'll be like, how the heck am I supposed to solve when there's 2 y's and you can factor it? I'd like you to also do number 20. And then that's it. We're not going to even go to the last page. I don't care. I know this is the important thing. 17 and 20. But you got to do them yourself. If you get stuck, ask for help. Question? Yes.
Can you just like not distribute for number 15? Yeah. And then just divide by x.
Oh, yes, you could have. And I was thinking number 16 was like, or 15 was like number 17. So here, let's just do 17. That's the one I keep on saying is going to be a big deal. Well, let's do that one. And then you can do 20 by yourself. This is y equals, okay, and then I switch x and y. So this is x, and this is a y, and that's a y. And the weird part is that you now have 2 y's. And they end up on opposite sides of the equation even. Because why? Because if you can factor it, you should, and I can't. So then I go to the clear fractions thing. So I'm going to multiply this by 3y plus 4. I'm going to do the other side by 3y plus 4. And this is an x. Don't forget the big red x there. Okay. And then this cancels this. And now, x times 3y is 3yx. X times the 4 is 4x equals 2y minus 1. And again, this is the one where people are like, how on earth are you supposed to solve for y? There's y's on both sides. Well, you get the y's all onto one side, and then you'll be able to factor it. If I hadn't said anything, I'm afraid too many kids would have just been completely lost. So I'm going to go a little further. Those cancel. 4x equals 2y minus 3yx. And then there's a minus 1 still. So let's get rid of that by adding 1 to both sides. That'll basically just move that over there. Instead of a minus 1, it'll be a plus 1. And right here, how do you solve for y when there's 2 of them? Well, I've said it enough times that if you can't do it now, I'm a little scared for you. Yes. And I get why that's a tough one, but it's my favorite saying for a reason. So I'm going to recopy the equation down here. 1 plus 4x is equal to y times 2 minus 3x. And now that you've got only one y, it's easy to get it alone. Divide both sides by 2 minus 3x. 2 minus 3x. And man, you had to be really good at algebra to do that. In fact, you practically had to be an algebra ninja. Figure that one out. And I'm ending on that.